Hi, my name is Ramaakshu Patel, and this is my final project on CNN on CIFAR 10 for ADTA 5550. For this project, it is required that the student is to use TensorFlow directly encoding to build, train, and test the CNN. The student is not to use Keras encoding and should only use TensorFlow version 1. For part 2, a dataset of images. The dataset I chose is called wildcats.csv. This dataset is for image classification tasks involving 10 distinctive big cat species. The total images in this dataset is 2,439, and out of those, 2,339 images are allocated for training set. Out of those, the 100 that is a difference from 2,439 to 2,339. 50 are used for testing and 50 are used for validation. This data set is collected from Kaggle, and the link is also provided. A little bit more information on the wildcats.csv file. This data set consists of 10 different classes, and each of those represent a different big cat species. All images were sourced from the internet, and they all mimic a real-world scenario. This dataset has proved to have high accuracy levels in numerous classification tests. Quick overview on CNNs. Convolutional neural networks are deep learning models designed for image processing and pattern recognition. They consist of convolutional layers that extract features, pooling layers that reduce data size, and fully connected layers for classification. Activation functions like ReLU and softmax help the network learn complex patterns. CNNs are highly accurate in image-related tasks. Automatically learning features without manual extraction. They are widely used in applications like facial recognition, medical imaging, and self-driving cars. A quick introduction into the beginning of this project. For this project, I focused on building, training, and testing convolutional neural network on CIFAR 10 dataset. This is a widely used benchmark for image classification tasks. The dataset consists of 60,000 color images that are categorized into 10 distinct classes, making this more complex than a grayscale dataset such as mints. For this project, the objective is to analyze the learning behavior of a CNN on CIFAR 10 by monitoring the accuracy progression over multiple steps. I also compared the CNN for CIFAR 10 to the CNN done for mints to see how they differ and evaluate why there were gaps between the two CNNs. To optimize the model's performance, I experimented with different hyperparameters. These included filter sizes and training steps aimed to improve the classification accuracy. By testing the two models, I created and evaluated how changes in the CNN architecture can impact the learning efficiency and overall model accuracy. Through this project, I aim to gain insights on how well CNN can perform on complex datasets and explore potential improvements to have better generalization. Part 3, obtaining the dataset for CIFAR 10. I began by navigating to Canvas and downloading the dataset CIFAR 10 dataset. With the dataset, there are 7 files that needed to be individually downloaded. Once I had them all downloaded and saved them on my home folder on my computer, I was ready to upload them. To do so, I first needed to connect the remote server through Google Cloud SSH. From there, I navigated to my Jupyter Notebook folder, and to upload all the files under one folder, I created a subfolder inside of the Jupyter Notebook folder. That folder was named CIFAR 10 data. Inside this folder, all the files were added one by one using the cp command. I then confirmed all the files are under the new subfolder by using the lsl command. And here is a screenshot of how it looks when it was uploaded correctly. This image confirms the dataset is properly loaded under the CIFAR10 dataset subfolder. Moving on to part 4. Building, training, and testing on CIFAR10. The architecture of this CNN consists of 5,000 steps, a filter shape of 44332 for the first convolutional layer, a max pooling layer, a 2x2 pooling, and a stride of 2. The filter shape for the second convolutional layer is 4432 by 64. The max pooling layer 2 is 2x2 pooling and a stride of 2. The fully connected layer is flattened input is 8 times 8 times 8 by 64. And the output layer is 10 neurons. Here are the results from the CNN. This CNN model presents an analysis performance metrics that are recorded at different steps during the training of the convolutional neural network. The goal of the CNN test is to identify trends and patterns in accuracy, as well as model improvements. From the results, I was able to see through the various steps there was a consistent upward trend, but this is not without its fluctuations. During step 0, the accuracy is 10%, which means that it's close to random chance. However, as the steps increased, by the 1000th step, I was able to see a spike in upward trend, which shows good and effective learning. When reaching the 2400th step, the model had reached a 68% accuracy. However, during the 2500th step, I noticed a decrease. Despite the fluctuation, the accuracy level was still increasing and staying steady. The highest recorded accuracy was during the 4000th step at 70%. And after that, I saw some more fluctuations, and the final recorded step showed a 69% accuracy. Overall, the data shows an effective learning progression of the CNN trained on CIFAR10 dataset. The model quickly gained accuracy in its early stages, and then became stable during the middle stages. Some improvements that may help increase accuracy are different filter shapes and possibly increase the number of steps used. Part 5. In part 5, we compare the convolutional neural network performance. In this part, I evaluated compared the performance of 2 convolutional neural networks on 2 popular image classification datasets, MINST and CIFAR10. The purpose of this is to collect the accuracy data from 50 different runs for each of the datasets. I also analyzed any gaps in performance between the 2 CNNs trained on the 2 datasets. A bit of an overview on the dataset. For the MINST dataset, it consists of 70,000 grayscale images. Each image is 28 by 28 pixels in size, making these simple in terms of size and complexity. On the other hand, the CIFAR10 consisted of 60,000 color images of 10 different classes. Each image was 32 by 32 pixels in size. The images in the dataset were way more complex and diverse. Both models were trained similarly. However, the MINST dataset had to be reshaped for it to be ready for the first convolutional layer. A little brief on the training setup. Both CNNs trained similarly. The MINST dataset was reshaped for compatibility with the convolutional layers, and the learning speed and accuracy was analyzed over 5,000 steps. Learning speed and accuracy for MINST. MINTs had a rapid learning curve. At step 100, accuracy was above 94%. For step 1000, accuracy surpasses 98%. And by step 3000 and onward, there was a near perfect classification with minor fluctuations. This showed that the CNN model was quickly learning and nearing a perfect classification just after 3000 steps. And there were only a few minor fluctuations in the later steps. Now taking a look at the learning speed and accuracy of CIFAR 10. For this CNN, there was a slower learning speed compared to MINTs. By step 1000, the accuracy reached only 61%. By step 4900, accuracy remained below 70%. Overall, the CNN struggled to improve beyond 70% due to the dataset complexity. The performance gap explanation. The CNN trained on MINTs achieves a near perfect accuracy because of how simple the dataset is. There's less background noise and limited feature requirements, which help the CNN perform well. While the CIFAR 10 struggled because of the complexity of the image features, it was not able to even exceed over 70% accuracy. The RGB images cause for deeper learning, and complex backgrounds make it harder for object detection. This gap in performance is mostly because the data sets are different in complexity. The MINTs dataset has the advantage of simplicity, and the CIFAR 10 dataset has the disadvantage of being super complex. Some key takeaways. MINTs CNN achieved near perfect accuracy quickly, and the CIFAR 10 CNN shows a steady improvement, but struggles with the complexity. Some future improvements. You can explore advanced techniques to improve CNN performance on complex datasets. You can also use deeper architectures, data augmentation, and advanced training methods. Then we can also enhance feature extraction for better classification on CIFAR 10. Quick conclusion on this CNN. The CNNs performed differently based on dataset complexity. Simple datasets like MINTs led to higher accuracy. Complex datasets like CIFAR 10 require advanced techniques for better performance. Moving on to part 6, improve convolutional neural network performance. This is where I made a proposal of modifying the filter size to 3x3 and increasing the training steps to 7,000. The CNN on CIFAR 10 only reached a maximum accuracy of 70%, which is low and can be improved by altering the code and possibly changing the number of steps. I propose modifying the filter steps to 3x3 and increasing the training steps to 7,000. Using a smaller filter size allows the network to capture more detail, spatial features, in the complex images of CIFAR 10. Also, increasing the training steps provides the model with iterations of refine its weights, allowing for improvement in conversions and classification accuracy. These adjustments are made to enhance the model's ability to recognize intricate patterns across 10 object categories. A quick overview. The CNN model for CIFAR 10 improved with proposed changes. The training and monitoring across 7,000 steps the initial accuracy was 9.68%, indicating random guessing. The significant improvement observed as training progressed. Early training phase from steps 0 to 1000 steps. The initial performance was a bit slow, starting off with only a 9.68% accuracy, which meant the model was doing more of random guessing. Although it started off slowly, by the time the 1000 step was reached, the accuracy had increased significantly. We can see here on our slide. Mid-training phase, steps 1000 to 4000. During the mid-training period, the accuracy continued to increase and had already surpassed the highest level of accuracy from the original CNN. At the 4000 step, the CNN accuracy was at 70.22%. This stated that the learning rate is effective. There were no significant drops. However, there were some fluctuations, but that did not affect the positive trend. Late training phase. This is for steps 4000 to 7000. From step 4000 and onwards, the accuracy fluctuated between 70 and 72%. And this was minor and not too much of a concern. The highest point of accuracy was recorded at 6000 step, coming in at 71.88%. Although there were some decreases around step 6400, the model was able to recover and gain back momentum. The final accuracy recorded at step 6900 was 71.33%. This suggested that the model had nearly converged. A quick performance analysis on this one. This model with the changes made showed strong learning progress in the first 4000 steps. But onwards, it was only small incremental increases. This indicated that the model was approaching its performance limit. In the later steps of the model, it seemed as if the model was overfitting due to the slight decrease. But again, it was only marginal. The model did perform better than the original model we started with. However, I think that was more because of the filter size change rather than the step count change. I feel like the filter size had a bigger effect, and the step count change actually made it feel like it was more overfitting. I'll go over some descriptions of each step that I did. For part 4, I implemented a convolutional neural network that is designed for image classification on the CFIR10 dataset. I trained the model for 5,000 steps, recording the accuracy at different intervals. For this CNN, the results showed a steady increase in accuracy. However, it was only able to reach a peak accuracy about 70%. These results also showed signs of fluctuations and a decrease in accuracy in the later steps. This indicated changes were needed for improvement. The description for part 5. In part 5, I evaluated the CNN performance on 2 different datasets. One of them was for MINT's dataset, and the other was done for the previous step on CFIR10 dataset. The MINT's dataset was a simpler and more and more consisted of grayscale handwritten notes, while the CFR10, as mentioned before, is way more complex and consists of color images. While comparing the two, I noted that the CNN and the MINTs performed very well, reaching 94% in the first 100 steps, and with the highest accuracy of 98%, while the CNN on CFR 10 required more steps and struggled to pass a 70% accuracy. This showed me that the complexity of data set really affected the performance of the CNN. Description on Part 6. In Part 6, I made observations on how the CNN performed on Steps 4 and Steps 5, and proposed a modification to the CNN to possibly improve the performance on CFR 10. For this, I began by reducing the filter size from 4x4 to 3x3, and doing so helped the model capture finer details. I also increased the training steps from 5,000 to 7,000, which allowed the model to have more iterations to refine its weights. Once these changes were made, I ran the CNN again for CFR 10 and documented the results. This time the highest accuracy reached was 71.88%, and it was recorded at the 6,000 step. The 71.88% exceeded the previous peak of 70% that was reached on the original CNN. On this new model, I also noticed fewer fluctuations, and it also demonstrated a bit more of a stable learning progression after steps 4,000 and onward. Although the training steps were increased, I still believe the biggest factor improvement was the filter size change. Conclusion for Part 4. For Part 4, the implementation of the CNN and CFR10 showed a clear trend of increasing accuracy over time. There were some fluctuations noted, however. As the model progressed, it quickly moved away from random guessing in early steps, and it demonstrated a steady learning progression. This model reached a peak of 70% accuracy, and it began to plateau as the steps progressed in the later steps. This suggested that the current architecture has limitations on extracting complex features from the dataset. This CNN highlighted areas of improvement, such as optimizing hyperparameters or modifying the network architecture. The conclusion for Part 5. In Part 5, the comparison of CNN on MINTs and CFR 10 showed the significant impact of how complexity in a dataset affects model performance. While the CNN on MINTs was able to reach a near perfect accuracy within the early steps, the CFR 10 required more training, and even then, it struggled to move past the 70% accuracy. Overall, the gap in performance suggests that grayscale and low complexity images are much easier for CNNs to classify. On the other hand, the colors in the images of CFR 10 requires more advanced techniques. From the results, I believe that CNNs need deeper architecture and possibly more complex feature extractions when working with a dataset like CFR 10 dataset. Conclusion for Part 6. For Part 6, the last part of the project, by modifying the filter size and increasing the training steps, I was able to successfully improve the CNN's accuracy on CFR 10. The highest recorded accuracy was during step 6,000, and it was 71.88%. Although increasing the number of steps allowed for further refinement of the model, the most impactful change was reducing the filter size. This enabled the network to capture finer details, Even with improvements in performance, the gains in accuracy were incremental. This indicated that future advancements are still needed. This phase demonstrated the effectiveness of fine-tuning a CNN, and it also provides insights for future improvements in image classification models. For this step, I also did a trial for just having 8,000 steps compared to 7,000 steps. But then I went with the 7,000 steps because I knew that it was already overfitting. When I lowered to 7,000 steps, I had much better performance, and that's why I went with the 7,000. In this project, I explored the design, training, and optimization of a convolutional neural network on the CFR10 dataset, which progressed through multiple phases to evaluate performance and identify improvements. At first, the model showed steady learning, but it did struggle to exceed a 70% accuracy level. This highlighted the challenges the CNN was having classifying the complex color images. I also performed a comparison with Mint's dataset to explore further in how dataset complexity significantly impacts CNN performance. The CNN on Mint's outperformed the CNN on CFR10 due to the simplicity of the grayscale images it consisted of. And this is the final conclusion of the overall project. Thank you.